Okay, all right. Okay. So I'm going to start the review by talking a little bit about projections and least squares. So I just wanted to cover some of the important information, and then after that, I'll have an example prepared after that one. Okay. So to start with, I'll talk about projections first. So here I've drawn a picture, and in this picture, this plane is representing like some subspace of Rn, which I'm calling W. I've drawn a vector B, and this vector B is sticking out of the plane, so it's like a vector that's not in the subspace W. So the projection of B onto W is this vector here that I've drawn in this kind of yellowish, goldish color. And then this vector here that I've drawn in red, this vector was usually called the error vector. And the error vector is actually just the difference between B and its projection. So E is just B minus P. And I guess like the most important properties of the projection vector. So one, the projection vector is the vector in W that is closest to the vector B. And then regarding the error vector, the error vector, as I've kind of drawn in the picture, is going to be orthogonal to W. So you have this little right angle there. And the length or the magnitude of the vector E represents this shortest distance between B and the subspace W. Okay, so that's kind of the significance of the projection and error vectors. And one of the applications of projections is least squares. So I'm going to talk about least squares a little bit right now. So when you have an equation ax equals b that has no solution, okay. So to say that this equation has no solution, that's equivalent to saying that b is not in the column space of A. So you have a picture that's pretty similar to the one I drew for projections, except here this plane is representing the column space of the matrix A. And then we have the situation where B is not in the column space, so it's like sticking out of it. Okay. So because this equation has no solution, one thing that we might want to do is try to get as close as possible to a solution. And the idea of that would be to, instead of looking at the equation ax equals b, we'll consider this sort of related equation ax equals p, where p is the projection vector. And here the idea is that since p is a vector in the column space of A that's closest to B, solving ax equals the projection p is kind of like the closest that we can get to solving the original equation ax equals b. Okay? Yeah, that's right. Yeah. If you can't see the screen, then yeah, I think I would recommend maybe like refreshing your screen, or possibly signing out real quick and signing back in. Okay. I think if everyone were having a problem, then I would know it was on my end. But right now, it sounds like you're the only one with a problem, so it's probably something on your end. Okay. All right. Now, so the solution to ax equals p is what we call a least squares solution to the original equation ax equals b. And I guess this class has been using x hat as like the notation for the least squares solution, okay? All right, so I'm gonna talk just real quick, like roughly what's the procedure for finding a least squares solution, and then I'll be illustrating with an example afterwards. So to find the least squares solution to ax equals b, what you want to do is you want to look at this equation, A transpose A x hat equals A transpose B. Maybe the easiest way to remember this equation is to take the original equation and multiply both sides on the left by A transpose. So I'm not going to go into the theory, but it turns out solving this will give you the least square solution. Okay. So you would solve this either by doing elimination, or sometimes if A transpose A is invertible, you might use its inverse to find the solution as well. And then I also wanted to talk about like finding the projection vector. And so I talked about how the least square solution is a solution to like AX equals P. So that means if you take A and multiply it by the least square solution, that product will give you the projection of B, although it specifically gives you projection onto the column space of A. Okay. All right. And if we use x hat equals A transpose A inverse times A transpose B, and I plug this expression into like this equation, you get this formula where the projection of B onto the column space of A is A times A transpose A inverse times A transpose times B. So I think you guys might remember seeing that formula a bit earlier in the semester. And this product, A times A transpose inverse times A transpose, that product was called the projection matrix, and they usually denoted it with a capital P. Yeah. So taking the projection matrix and multiplying with B gives you the projection of B onto the column space of the matrix A. Okay. And then lastly, if you just want to find a projection onto any subspace W, the idea of that is to first find a basis for the subspace W. If you take those basis vectors and you put them into a matrix A as columns, then essentially what will happen is the column space of this matrix A would be the subspace W. Oops. And then you just get the projection of B onto W by calculating the projection of B onto the column space of this matrix A. Okay. And I'm going to illustrate all of that with an example in about a minute. There's one more thing I wanted to touch on. I don't know how important this is, but it's a relatively simple fact, so I thought it was worth mentioning. I don't think I ever mentioned this in my reviews, but you guys might have talked about it in your class. So I also wanted to briefly just talk about projection onto the orthogonal complement of a subspace. So here I kind of have like the usual projection picture. W is some subspace. I've added the orthogonal complement of W into the picture though. So this line that I've drawn, the line in black there, that line is representing the orthogonal complement of W in my picture. And then the error vector, which I usually draw here, I've drawn the error vector over here instead. So it's kind of like attached at the origin, which is this point. And so what I wanted to kind of point out in this picture is that if you kind of look at it, you'll actually see that the error vector is a projection of B onto the orthogonal complement of W, okay? And so therefore, if you want to calculate projection of B onto like the orthogonal complement of a subspace, one way you can do that is just by computing this error vector, okay? So that's such a very quick review of like projections and least squares. And so I'm going to start an example with that now. Okay. Okay, so this question that I'm about to do, I thought this would be kind of fun. So this is actually one of the questions on the exam that we give to people who are applying to be a tutor for peer tutoring. So I thought it might be cool for you guys to see, like maybe an example of a question that we ask potential tutors. Okay, so here we have some data points given, and it's not too important, but I've plotted the points in a picture over here. So we were given the point 1, 6, 2, 3, and 3, 3. Okay, let's see here. Can I zoom in a bit? Sure. Okay, I see. I guess it's kind of a small. Zoom in. All right, is that good?
Yeah, it looks fine.
Okay, all right. Let's see here. Okay. So in this problem, basically the first two parts of the question are asking us to find the line that will like best fit these three data points. Okay. And so the first part of this question is asking us if we wanted to find an equation of the line y equals cx plus d that passed through these data points. For the line to pass through the data points, that means that all three of them would have to satisfy this equation. So what I'm going to do is I'm going to take these three data points and just plug them into here for x and y. So the first data point, when x is 1, y is equal to 6. Okay. Second data point, when x is 2, y is equal to 3. And then the third data point, when x is 3, y is equal to 3 as well. Okay. And then, so here, this kind of gives us a system of equations to try and solve for C and D. And I'm going to rewrite it in matrix form. So I'm going to write it as like a x equals b. Okay. So here the unknowns in the system of equations are C and D. Okay. A is the matrix of the coefficients. So here we have coefficients 1, 1, 2, 1, and 3, 1. Okay. And then B is going to represent the other side of our equations, which are, in this case, 6, 3, and 3. Okay. All right, so if we were looking for a line that passed through our three data points, then the C and D in the equation will have to satisfy this system of equations. And that's kind of all the part A was asking for here, just asking us to write out the equation AX equals B. Now in part B, the idea here is these 3 points don't actually lie on a straight line. And because of that, this system of equations that we have in part A will have no solution. And so if this equation has no solution, we're going to do the next best thing and find the least square solution instead. And then when we find the least square solution, that will also give us the equation of the line of best fit. So let's see how that will work, okay? So I talked about it earlier, but to get the least square solution, you want to look at this equation, A transpose A x hat equals A transpose B. So what we'll need to do first is we'll need to compute A transpose A and A transpose B as well. So I'll do those computations first. Okay, so A transpose, I'm going to transpose A. So I'm going to just take the columns and write them as rows. It's A transpose and then times A. Let's do the matrix multiplication. So we're going to get 1 plus 4 plus 9 is 14. Okay. Next, we're going to get 1 plus 2 plus 3 is 6. Then we'll have 1 plus 2 plus 3, so 6 again. And lastly, you'll get 1 plus 1 plus 1 is 3. Okay, so that gives us A transpose A. We're also going to need A transpose B as well. So let me do that computation next. Okay, so here's A transpose again. And we're going to multiply it with vector B, which was 6, 3, 3. Okay. So here doing the multiplication, it'll be 6 plus 6 plus 9, which will be 21. And then we're going to get 6 plus 3 plus 3, which is 12. Okay. So now that we have A transpose A and A transpose B, let's take a look at what this system of equations will look like. So on the left, we have A transpose A times x hat. So for x hat, I'll use this notation like c hat and d hat, I guess. So we're not solving for like the actual c and d because there's actually no solution to this system of equations. So I guess I'll call x hat a c hat d hat instead of cd. Okay. So A transpose A x hat. And then A transpose B we found was 21, 12. Okay. And now what I want to do is I want to solve for x hat. So to solve for x hat, you can solve this by doing elimination, or since it's a 2 by 2, there you go. For me personally, I have a formula for the 2 by 2 inverse memorized, which I'm going to write out here right now. So like a B, C, D, the inverse of that, I know it's 1 over the determinant times, and then I know you swap the diagonal entries, and then you change the sign of the off-diagonal entries. Okay. So since I have this formula kind of memorized, I think I'll use it to solve for x hat right now. So to solve for x hat, we need to multiply A transpose A inverse to the other side of the equation. And then let me see what that was. Right, so yeah, for 2 by 2, I find it kind of convenient to have that formula memorized because it just kind of automates some of the work, I feel like, if you have that formula memorized. Okay, and so then I'll apply the formula now. So the inverse of this matrix is 1 over the determinant. So the determinant is going to be 14 times 3 is 42 minus 6 times 6, so 36. So 1 over that. I'm going to swap the diagonal entries. And then I'm going to change the sign of the off-diagonal entries. Okay. then we have 21 and 12 here. Okay, so let's see. So here we have 1 over 6. And then 3 minus 6 minus 6, 14 times 21, 12. Okay, so here let's do the matrix vector multiplication. So we're going to get 3 times 21, which is 63. Minus 6 times 12, so minus 72. And then here, negative 6 times 21 is negative 126. Plus, and 14 times 12, I think that's 168. Is that right? Okay. And then, so 63 minus 72 is negative 9, right? And then negative 126 plus 168, that's 42, I think. Okay. So then if I did my arithmetic correctly, then this would be our least square solution, C hat and D hat. Okay. Yeah, so you could definitely do row operations as well. So it's up to you how you want to do it. I like using the inverse, at least for a 2x2 case. Although if it were larger than 2x2, I would have done the row operations as well, okay? All right. So then in particular, we have C hat. It looks like it was negative 9 over 6, which I guess we can simplify negative 3 over 2. And then D hat was 42 over 6. So we can simplify that to be 7, okay? And then now that we have C hat and D hat, we can also write out our equation of the line of best fit. Okay. So the equation should have the form y equals cx plus d. But we're using our least square solution, C hat and D hat. Okay. So that means the equation of the best fit line will be negative 3 halves x plus 7, okay? So here, that gets us the least square solution, and then also the equation of the line of best fit. Okay. So let's go back to the question. So right now that takes care of parts A and B. So let's take a look at the rest of the problem. So parts C and B as well. Paste it here again so we can reference it. Okay, so now part C is asking us to find the projection of the vector 6, 3, 3 onto the column space of the matrix A from part A. Okay, so let's go back to A, part A of the question. So this is the matrix A that we were using. So let me also copy this down to there for reference. All right, so this was the matrix A that we were working with. So then in part C, when they are asking for the projection of the vector B which 633. I'll just write that down. Okay. So we have B 633. So it's not a coincidence the way that I designed the problem that vector B was this 633 was the vector B that we had. And I'll kind of explain what I had in mind for parts C and D when I created this question. Okay, so right now, part C, they're asking you to calculate the projection onto the column space of the matrix A of the vector B. Okay. And so I talked about how to calculate this projection vector. So one way you can do it is you could certainly just use this formula. To calculate the projection of B onto the column space of A. But the idea that I had for this problem is that you can calculate the projection just by doing A times the least square solution as well, right? So that's what I talked about earlier at the beginning of the review. So really, like this whole A transpose A inverse A transpose B part is the least square solution X hat. And we already calculated the least square solution earlier just now. So what we had for the least square solution X hat was -3/2 and 7 for the C hat and D hat. So the simplest way to calculate the projection of this vector 633 onto the column space of A would be to just take the least square solution that we found and multiply it with vector A, okay? Sorry, matrix A, not vector A. So I'm just gonna do A times X hat. Okay. So if we do this computation, we're gonna get -3/2 plus 7. So -3/2 plus 14/2. So I believe that's 11/2. Here we're going to get -3 plus 7 is 4. And here -9/2 plus 7, I think that's +5/2. Okay. All right. So then here, this would be the projection of B onto the column space of A. Now, if you maybe like just forgot about being able to compute the projection by just taking A times the least square solution, then certainly you could have just used this formula as well. It just, you would have been kind of repeating a lot of the work that you already did because you already kind of multiplied all of this out to get X hat in the first part. So if you do all the multiplication again, you'll get the right answer, but it maybe just would have taken a little bit longer, okay? Right. So I like when I get to like this question, when I'm like grading the exams, I like saying which of the people computed projection by doing this and which people computed the projection by doing this. And I have sort of a sense that maybe the people who computed doing this might have like a better understanding of least squares and projection and how they relate to each other. So I kind of like to do this kind of like a see, you know, how are they solving it, and from there I can somewhat get I can kind of guess like maybe how good their understanding is from that. So that's why I like this question. Okay, and then let's look at part D as well. So part D is also a question that you can kind of solve in different ways. but it's asking us to find the projection of the same vector B, 6, 3, 3. But this time they want the projection not onto the column space, but onto the left null space of the matrix A, okay? So for this question, in my mind, there's kind of two ways you can go about it, and I'll kind of explain what the two methods are. So the first thing that you can do for this problem, to project onto a subspace, I described the procedure for doing that earlier. The first thing you'd want to do is find a basis for whatever subspace you want to project onto. In this case, we're trying to project onto the left null space of A, which was the null space of A transpose. So what we could do is get a basis for the null space of A transpose, take the basis vectors and put them into a matrix as columns. I'll call the matrix B, since we're already using A in the problem. So then the idea is that the column space of this matrix B would be the left null space of A, since the columns of B were a basis for the null space, the left null space of A. So then you can use the projection onto a column space formula So B times B transpose B inverse times B transpose and then times vector B. And this would give you the projection onto the left null space of A. Okay. There's kind of an alternative way of doing this problem as well. So the alternative way that I kind of want to show you guys is, so left null space, if we remember how the fundamental subspaces of a matrix relate to each other, you might recall that the left null space is actually the orthogonal complement of the column space. And likewise, the null space was the orthogonal complement of the row space. And so another way that you can approach this question of projecting onto the left null space is, if I just go back to here real quick. I talked about it at the bottom, but when you're projecting onto the orthogonal complement of a subspace, the projection onto the orthogonal complement is just the error vector. So an alternative method of solving out part D of this problem is to just take the vector B and subtract its projection onto the column space. Okay. So B minus the projection gets you the error vector, and the error vector was the projection onto the orthogonal complement, which in this case was the left null space. Okay. So probably the most efficient way of going about this problem, since we already computed the projection of B onto the column space of A in the previous part, you should be able to calculate the projection onto the left null space by simply taking the vector b, which was 6, 3, 3, minus its projection, which we calculated here as being 11 over 2, 4, and 5 over 2. Okay? All right. Okay. Let's finish up this computation. So 6 is 12 over 2. 12 over 2 minus 11 over 2 is 1 over 2. 3 minus 4 is -1. And then that's 6 over 2 minus 5 over 2 is 1 over 2. Okay. And then that gets you the projection of B onto the left null space then, all right? So I don't know if you guys have any questions right now. I'll pause for a moment. Sure, so if we're gonna look at method 1, so what you'd want to do to get a basis for the left null space is, what I would do for that first part is just transpose A first, because we want to look at the null space of A transpose. Okay. And then if you remember how to calculate null space, essentially you want to start doing some row operations and reduce the matrix a little bit. It's not super important, but I kind of like the idea of swapping rows because I just feel like it looks better to have the ones on the top. But that's not too important though. As long as you just do the elimination, in this case, row 2 minus row 1 will give us the 0 that we want there. It'll be 1, 2, right? And then this is good, but if you want to go all the way to the reduced row echelon form, you could do row 1 minus row 2 real quickly to eliminate the zeros above this pivot, or to eliminate everything above this pivot. So if we did that, you would get 1, 0, 0, 1. And then row 1 minus row 2 gives us -1. Okay. So here I took A transpose, I row reduced it. And then the way that I get the null space is I convert this into a system of equations. So like here, the first row, I would maybe read it as like 1x plus 0y minus 1z. And for null space, you set it equal to 0. And then second row gives you y plus 2z is 0. And in this case, what would happen is the way that I would go about this is the third column is missing a pivot. So I would choose z to be the free variable. And I know everyone does this slightly differently, but the way that I tend to do this is I assign a parameter. So it's kind of like a dummy variable to my free variable. So I'm just going to say z is t. And then I'm going to do sort of back substitution. So I'm going to substitute t in for z into the equations. So z is t, you're going to get y is -2t. And then likewise, if z is t, you'll get x is equal to t. Okay. So the solution, x, y, z, I can write it as t times the vector 1 minus 2 and 1. So I just took the coefficients 1, minus 2, 1, and factored the t out. And this vector that we ended up with, 1, minus 2, 1, would have been a basis for the In this case, we were looking at the null space of A transpose, so the left null space of A, okay? So then what you would have done is take that matrix, take that vector, put it into a matrix as a column, and then you could go through this computation here to work out the projection of B onto the left null space. Okay. And you should get the same answer as this over here. Right, so then both methods will give you the same answer, of course, okay? So whether you do this computation or whether you simply just use the error vector, it should give you the same answer in the end, okay? All right, but I might come back to this later if you guys want, but I think it'll be useful to continue because I have like a lot of stuff to cover as well. So I'd like to move on to the next topic, which was just talking about Gram-Schmidt. Okay, let's move over here. Okay, so a quick review of what Gram-Schmidt was before I do a little bit of an example. So let's say that you have some vectors v1 through vk. So these are maybe vectors in some Rn. Okay. What Gram-Schmidt does is it takes a given set of vectors and it sort of creates a new set of orthogonal vectors. Okay. Oh, that's kind of weird. Okay. And here I've written out what the formulas for Gram-Schmidt are. So if you have like vectors v1 through vk, Gram-Schmidt will compute a new set of vectors w1 through wk. These vectors that it creates are going to be orthogonal to each other. And the way it works is you're going to start by setting w1 equal to v1. And then to make sure that w2 is orthogonal to w1, you're going to take v2 and subtract its projection onto w1. And that gets you vector w2. And then you kind of repeat the procedure. So for w3, you're going to take v3 and you're going to subtract its projections onto w1 and w2 to make sure that the result is orthogonal to w1 and w2. And then kind of like etc. I like to think that you won't need to do Gram-Schmidt with more than 3 vectors. So I figured it was probably good enough to just write out the first 3 equations explicitly, okay? Here for the projection of B onto A, you could use the projection formula that we talked about earlier, but so you could do like A times A transpose A inverse times A transpose times B. But for the special case where you're just projecting onto like a line or just onto like a vector, I like to rewrite the formula like this instead in terms of dot products, just because for me, I guess I find it much easier to think about dot products than to think about all the like matrix multiplication, okay? But these formulas, they are equivalent. Okay. So you could certainly use like the formula written out in this way to calculate the projection. I just think it's easier to calculate it this way instead. So that's what I plan on doing in my example, okay? Here in the denominator, when you have a vector dot product with itself, I thought it was worth remembering that vector dot product with itself is equal to its magnitude squared. So that's why I rewrote the formula like this. So either way is fine. All 3 of these formulas are the same, okay? So I mentioned already that Gram-Schmidt, the vectors, the W's, those vectors that it produces are going to be orthogonal to each other. There's another really important property about Gram-Schmidt that we don't really talk about much, but we secretly are actually using it all the time, even if we don't really talk about it that much. But the vectors that Gram-Schmidt produces, they share the same span as the original set of vectors. So that's actually a pretty important property of Gram-Schmidt. And then here, one of the reasons why we talk about Gram-Schmidt, like why it's important, is because sometimes it's easier to work with your vectors when they are orthogonal. And one result that kind of reflects that is this fact that I wrote down here. And so if you have a set of orthogonal vectors, W1 through WK, and let's say that V is in the span of those vectors, then you can calculate V as being the sum of its projections onto the orthogonal vectors, okay? And this kind of gives you a simple formula, if you will, for expressing V as a linear combination of the vectors W1 through WK. So here, like if I were to kind of like plug in the formula for projection, so like here's like projection of V onto W1. And then likewise projection of V onto W2. If you plug in the formula that I wrote down earlier, you would have that and so forth. Okay. All right, so then when your vectors are orthogonal, at least in theory, it's easy to express a vector as a linear combination of them because you just use the projections and add them up, okay? And we'll see that in an example as well. I also wanted to highlight kind of a special case of this fact, which is if your vectors are not only orthogonal, but if they're also orthonormal, okay? And in case you guys don't remember what orthonormal means, so orthonormal means that the vectors are orthogonal to each other. And it also means that all the vectors are also a unit length, meaning their magnitude or their length is equal to 1, okay? So if you have an orthonormal set of vectors, what happens in this formula is the denominators will all be equal to 1 because they'd all be unit lengths if they were orthonormal. So then this formula kind of simplifies down to this when they are orthonormal, okay? So let me see what that was. All right, see, I think someone had a question, is that right? Yeah, what's your question? Not sure if you're trying to talk, but your mic is muted if that's the case. Not a problem. Did you have a question? Okay, sure. That's kind of a good question. I'm not sure if any formulas would be given on the exam. That would have to be a question that you'd ask your professor, okay? There you go, okay. Yeah, that's right, yeah. So because when your vectors are orthonormal, so their length would be equal to 1. So the denominators would be equal to 1. So if I just like drop the denominator from what I wrote down here, you get this formula for expressing a vector v as a linear combination of some orthonormal vectors, okay? Okay, all right. So then with that kind of a brief overview of Gram-Schmidt, let's take a look at the example that I have prepared. So I kind of have two parts to this. Here's part A. And what color was that? I think it was this one. Oh, that's convenient. I guess also, yeah, if ever the text is too small for you guys, I can zoom in on my end, but you're also able to zoom in just through e-learning as well. So maybe just real quickly, in the like upper left corner of your screen, there's kind of like two buttons that you can click on that will pull up a menu. If you click on the circular icon, it pulls up a small like little menu with 4 options. There's like a magnifying glass, and if you click on the plus button, it zooms in. If you click on the minus button, it zooms out. So if you guys are able to see that, it's like a small circular button that you can click towards the top upper left corner of your screen. You can use that to zoom in whenever my work might seem a little bit too small. And then I can also zoom in through OneNote if you let me know that it's too small as well, okay? Okay, all right. And yeah, I do apologize a little bit. I have a natural tendency to write really small, so okay. But here, let's look at this question. So we have 3 vectors given in R4, so v1, v2, v3. And this question is asking us to find an orthonormal basis for the subspace spanned by these 3 vectors, okay? So essentially what we want to do is we want to start by doing Gram-Schmidt to get an orthogonal basis. And so we're going to have to compute 3 vectors, w1, w2, and w3. The first one's the easy one, so w1 should just be equal to v1. Okay, so that's just using the formulas that I have here is what I'm going to be doing to compute w1, 2, and 3. So w1 is v1, so we have w1. Next, we need to compute the w2 vector from Gram-Schmidt. So according to this formula, w2 will be v2. So I'm going to take v2 here. And then we have to minus the project v2 onto w1, okay? So here's the formula for projection of b onto a. So for projecting v2 onto w1, I'll write it out first symbolically. So we're going to do w1 dot product with v2 over w1 dot product with itself times w1, okay? And then we have to do the computations now. Let's move over a little bit. Okay. Minus, okay. So here for the dot products, w1 dot product with v2. So the dot product is going to be 1 times 0 plus -2 times -5. So 0 plus 10 so far, plus 0 times 1 plus 1 times 2. So 0 plus 10 plus 0 plus 2 is what I got from the dot product there. W1 dot product with itself would be 1 times 1 plus -2 times -2, which would be plus +4, plus 0 times 0, and plus 1 times 1. So those are the dot products. And then we're going to multiply with W1, which was 1, -2, 0, 1. Okay? So let's simplify what we have. Okay, so here we have 12 over 6. So 12 over 6 is going to be 2. So finally, we have a 0 minus 2 is -2. This is going to be -5 plus 4, so -1. 1 minus 0 is 1, and 2 minus 2 is 0. Okay? All right. So I guess I'll write down the result here again, just so we have everything in one place. So we have W1, and now we have W2. And then next we will need to calculate W3. Yeah. Now before I get to that, remember that W1 and W2 are supposed to be orthogonal to each other. So I think when you're doing Gram-Schmidt that it is worth checking your work by checking to see if your vectors are orthogonal at each step. Sure, yeah. So when you say the sum in W2, which part of the work are you talking about? This part here? Okay, sure. So remember that the dot product of two vectors, let's use red, okay. Yeah, so remember when you have like two vectors, that their dot product was, you multiply their components together and then you add everything up. So it's like U1 times V1 plus U2 times V2 plus U3 times V3 if you had more components and so forth. Yep, yeah, that's correct, yeah. And yeah, so I was gonna do that actually anyways, because what I was saying earlier is I think it's useful to just double check your work. So here we want to maybe confirm right now that W1 and W2 are orthogonal to each other. And yeah, so remember that two vectors are orthogonal if their dot product is 0. And if we do the dot product, it's going to be like 1 times -2 plus -2 times -1. So that's going to be plus a +2. And then you have plus 0 times 1, yeah, and plus 1 times 0, okay? So it's very easy to make a mistake when you're doing Gram-Schmidt. And I therefore suggest that you check your work at each step, just to make sure that your work is good before you proceed, okay? Because in order to calculate W3, we're going to need to use W2. So if your W2 is incorrect, your W3 is going to be incorrect as well, okay? So I would sort of recommend myself that you double check your work. So here, the formula for W3, it's whoops, let me switch colors just to be consistent. So W3, we're going to take V3 now and subtract its projections. onto W1 and W2. So let's plug in some of the numbers now. So V3 was 8, 4, 2, -6. For the projection of V3 onto W1, so for convenience, I'll write out the formula. So it's W1.V3, W1.W1 times W1, which was 1 minus 2, 0, 1. And then let's see here. Projection of V3 onto W2 is going to be the same thing, but with W2 instead of W1. All right, and W2 minus 2 minus 1, 1, 0. Okay. And then we'll work out the dot products, and then we'll just do all the subtraction after that. Okay, so first W1 dot product with V3. Okay. So that's going to be 1 times 8 is 8. Plus -2 times 4. So that's actually plus a -8. Plus 0 times 2 is 2. Sorry, is 0. 0 times 2 is 0. And then plus 1 times -6. So plus a -6, okay? V3 is oh yeah, okay, yeah, okay, cool. And then let me see, so W1 dot product with itself, we did that earlier, it looks like it was 6. Okay. All right. And then let's do the dot products, W2 dot product with V3. So that's going to be -16 minus 4 plus 2 and then plus 0. And then W2 dot product with itself would be -2 times itself is +4. -1 times itself is +1. 1 times 1 is 1. And then you have a plus 0 at the end. Okay. So we're almost done. Just a little bit more. Okay. So here, 8 minus 8 will cancel. We have -6/6, which is -1. But then you have minus a -1. So I guess it's going to be plus. Okay. Over here, this is -20. Plus 2 is -18 over 6. So that's minus a -3. So let's make that plus 3. And then multiplying -2 minus 1, 1, 0. Okay. And then I'm just going to do the addition and subtraction now. So 8 plus 1 is 9, minus 6 gives us 3. Okay. 4 minus 2 is 2, minus 3 is -1. 2 plus 0 is 2, plus 3 is 5. And -6 plus 1 is -5, plus 0, so you have -5 at the end, okay? So W3 is 3, -1, 5, and -5. Okay. So then this is the results of Gram-Schmidt. Okay. So right now this will give us it should give us an orthogonal basis. To the span of the original vectors. You can kind of double check that W1 dot product with W3. That dot product should be 0, as they should be orthogonal to each other. Likewise, you could and probably should check the W2 dot product with W3. Whoops. Is 0, okay? So I won't work it out, but if you check the dot products, I think it works out. Yeah, it seems to work out. Okay. Now, this question did ask for an orthonormal basis, though. So to get an orthonormal basis, not only do we want vectors to be orthogonal to each other, but we also want them to be unit length, to be like orthonormal, okay? So now what we'll need to do is we'll need to normalize these vectors to get an orthonormal basis. So then if you remember what it means to normalize a vector, it means to take these vectors and to divide each of them by their length or their magnitude. So if I take W1 and I divide it by its magnitude, and then in case you guys don't remember, the length of a vector was the square root of the sum of the squares of its components. So I'm going to compute the magnitude of W1 right now. It's going to be square root of 1 squared plus -2 squared plus 0 squared plus 1 squared. So it'll be square root of 6. So if I take W1 and divide it by its magnitude, that gives me a unit length vector right now, which I'm just calling Q1. Likewise, I'll take W2 and divide it by its length or its magnitude. So here, its magnitude is square root of 4 plus 1 plus 1, so it's 6 again. And then I'm going to take W3, and again, to get an orthonormal basis, I need to normalize it. So the magnitude of W3 would be the square root of 3 squared is 9, plus -1 squared is 1, plus 5 squared is 25, and then -5 squared is another positive 25. So it looks like we get square root of 60 at the bottom, okay? All right. So then this here will give us an orthonormal basis for the subspace that was spanned by the original V1, V2, and V3, okay? All right. Now, if the question just asked for an orthogonal but not orthonormal basis, then you could have just stopped at W1, W2, and W3. But for orthonormal, we had to do this extra step where we normalize each of the vectors by dividing by this, okay? Okay. There was one more part that I wanted to do. I guess let's try to, maybe I won't work this out all the way, but I'll at least get started. It's pretty short, so that's true. Yeah, orthonormal is orthogonal, but orthogonal, and then in addition also unit length. That's right. Yeah. All right. So then for this second part of the example that I wanted to do, so I had this vector v, -3, 1, -2, and 2. This part is not super important, what I did here, but what I was doing specifically is I wanted a vector v that was in the span of these vectors. So I just picked a random linear combination of v1, v2, v3 to get a vector v, okay? But this part is not super important for the question, aside from letting us know that v is in the span of these vectors, okay? What I really wanted to do with this question was to express v as a linear combination of the orthonormal bases that we found in part A. Probably this one. Okay. So the idea of this question alludes back to what I talked about over here, about like one of the like advantages of having like an orthogonal basis or an orthonormal basis. Okay. So here in particular, since our vectors are orthonormal, we can express v as a linear combination of them just by doing these dot products. So let's illustrate how that works over here. So we can say that v should be equal to v dot product with q1 times q1 plus v dot product with q2 times q2, and then plus v dot product with q3 times q3. Okay. Okay. And I guess I'll at least do a little bit of the work for this. So we're going to do v dot product with q1. Okay. You can leave the 1/6 just in the front, and then just dot product like the actual like vector part, if you will. So I'm just going to do 1 times -3 is -3, plus -2 times 1 plus 0 plus 2. So we have that times q1. And then likewise, when I do v dot product with q2, I'll just leave the 1/6 in the front. And I'm just going to do -2 times -3 plus -1 times 1 plus 1 times -2 plus 0 times q2. And then just lastly, v dot product with q3, we'll get, so I'll leave the 1/60 in the front. And then that's -9 minus 1 minus 10 and minus 10 v dot q3. Okay. So I think altogether I have -3/6 q1. That's plus 3/6 q2. -30/60 q3. And then this would be v expressed as a linear combination of the orthonormal basis that we found in part A, okay? Yeah. So then that equation, I got it from this stuff over here earlier. And so specifically, if they are orthogonal, you can use, whoops. So if they're orthogonal, you can use this equation up here to express V as a linear combination of those orthogonal vectors. But then if they are orthonormal, then the equation simplifies a little bit. Because if they're orthonormal, then the denominators are equal to 1. So you just drop the denominator from the formula and you get this, okay? Yeah, so I'll pause for a little bit there. Any questions about any of that? Okay, all right. Let's see here. Let's go on to the next kind of major topic is determinants. Let's see here. How to get the part in parentheses. Yeah, let me see. Let's see here. So the stuff in the parentheses would have been the dot products. So let's go back to that real quick. So here we have to do V dot product with Q1. So I was taking the components of V and the components of Q1 over here and just multiplying them. So the 1 times -3 gave me the -3 and then kind of so forth like that. All right, is that good? All right, cool. Okay, so let's see here. Let's talk about determinants next. All right. So I have a little bit about determinants here. So first, determinants are only defined for square matrices. Okay. For the determinant of A, we kind of have like 2 different notations for it. So you sometimes see this notation that kind of looks like absolute value. But that notation it just means the determinant of A, okay? I think it's kind of important to remember sort of like the geometric interpretation of the determinant, which is that the determinant of a matrix gives you the signed, like for an n by n matrix, it gives you the signed n-dimensional volume of the n-dimensional parallelepiped formed by the n columns of A, okay? Signed means that determinant could be plus or minus the volume. The sign corresponded to the orientation, but I don't think that's super important to talk about, okay? For 2x2 matrices, remember we had this simple formula, AD minus BC for the determinant. For larger matrices, there's a couple different ways of computing determinant, which I'll get into here. Okay. So the first method was a method called a cofactor expansion. Okay, so for a matrix A, we define the ij cofactor of A, okay, which I denote by Cij. It's equal to -1 to a power of I plus j times the determinant of the matrix obtained by removing the ith row and the jth column from A. -1 to the I plus j is going to be either +1 or -1. And you can actually determine whether it's positive or negative by remembering this kind of sign pattern. So if you start with plus in the first entry and then alternate along the row and the column, and then just continue alternating along the rows after that. These plus minus signs tell you whether like -1 to the I plus j will be positive or negative, according to like which entry or which position you were looking at in the matrix, okay? And most of you, I think, probably know how to compute determinant using cofactors, but I'll illustrate with the example that I have set up over here right now. So to compute the determinant of a matrix using cofactors, you want to pick any row or any column of your matrix. Here, let's say if I pick the first row to start with. So the way this works is you're going to take each entry in the row or column that you picked, and you're going to multiply each of them with the corresponding cofactor, and then you're going to add everything up. So for the first row, I'm going to take the first entry, the 2, and then I'm going to multiply it by its cofactor. So to get the cofactor, you need to cross out the row and the column. So here I cross out the row and the column containing the 2. And then I have this 2 by 2 matrix remaining when I do that. And we're going to need the determinant of that one, okay? Next, I would do like -1 times its cofactor, and its cofactor will have a negative in front of it. So we're going to have like minus and negative, so I'll make it a plus. Okay. And then after that, I need to cross out the row and the column containing that -1. That leaves us with this 2 by 2 matrix. And then lastly, I would take the 0 at the end of the first row and multiply it by its cofactor, which won't have a minus in front of it. And then I cross out the row and the column containing that 0. We have this 2 by 2 remaining. And then we just need to work out the determinants and then just kind of add everything up. So of course this one is 0, so I maybe didn't have to write it out completely, but I thought I would write it out just so we could see it. And then for the 2 by 2 determinants, it's AD minus BC. So here this gives us 2 times 4 minus 0. And then here we're going to have 12 minus a positive 2. Okay? So it looks like we got 8 plus 10, so the determinant is 18. Okay? So that was computing the determinant using cofactor expansion along the first row. And you could compute the determinant choosing any row or any column. And then, yeah, so for these 2 by 2 determinants, the formula is A times D minus B times C. Okay? All right. And I'll do one more computation. So just to kind of make this part clear is you don't have to choose the first row to do the cofactor expansion. You can choose any row or any column. So let's just say as another illustration, if I were to do cofactor expansion, but say along, maybe I'll choose the second column, just to illustrate. Now we should get the same answer of 18 when we do this, okay? But if I did cofactor expansion along the second column, yeah, that's right. So here, let's see here, along the second column, I'll choose the first entry, which is the -1. I need to multiply it by its cofactor. Now, its cofactor will have a minus in front of it, so I'm going to change that to a plus. And then cross out the row and the column. And we have the 3 minus 1 minus 2, 4 remaining. Okay. Next, we have the 1. It'll just be plus, okay? And then we have to cross out the row and the column containing that 1. So that leaves us with 2, 0, -1, 4. The last one would come with a minus, but it's going to be 0 because of the 0 that we have in the matrix. Okay. And then just working this out, you're going to get 12 minus 2 is 10. Plus in here 1 and then 8 minus 0. So you get another 10 plus 8. So you get the same answer, okay? So if you pick any row or any column and do this cofactor expansion, you should get the determinant. So just pick the one with the most zeros in it, as one of the students said earlier. Because as you can kind of see, if there are zeros in your matrix, that will simplify some of the computation that you need to do, okay? So pick the row or the column with the most zeros is ideal, but you can pick any row or any column to get the determinant, okay? Yes, that's right. Okay, so cofactor expansion is like one method of getting determinant, and I think it's maybe the one we tend to use the most. That said, another way of calculating the determinant is by using row or column operations. Okay. So here, I've kind of here I've kind of talked about how row operations affect the determinant of a matrix. So there's kind of like 3 types of elementary row operations that you can perform when you're doing elimination. So one type of operation that you can do is you can swap 2 rows. So let's say we take A, we swap 2 rows, and that leaves us with a matrix B. The determinant of B is going to be the negative of the determinant of A. Okay. So essentially, swapping 2 rows changes the sign of the determinant. Okay, that's what this first one is saying. Likewise, if we take A and we multiply one of its rows by a constant K, the determinant of the resulting matrix will be K times the determinant of A. And maybe most noteworthy is if you have a matrix A and then let's say you add a multiple of a row to another row, the resulting matrix will have the same determinant as that of A, okay? So that's kind of a summary of how row operations affect the determinant of a matrix. And we don't do column operations that much, but the same is true of column operations as well, though. So if you're computing determinant, you could try to simplify the matrix by doing row or column operations, okay? But like swapping 2 columns would change the sign, multiplying a column by K, the resulting matrix would have determinant K times the original. And likewise, adding a multiple of a column to another column has no effect on the determinant, okay? So in addition to these facts about how row and column operations affect the determinant, another fact that I think is useful to know is that the determinant of a triangular matrix is equal to the product of its diagonal entries. So whether it be lower triangular or upper triangular, if it's either of those, you can calculate determinant easily. Just multiply the diagonal entries together, okay? Yeah, so it's just using row or column operations is just another way of calculating determinant. So I wouldn't say that there's ever a case where one method will work but the other won't work. What I will say though is usually if I have anything larger than a 3x3, I have a personal preference to do some row and column operations first in order to calculate the determinant, because I feel like that's easier. I think you should know the first two methods of calculating determinant, just because they could easily ask you to calculate determinant using this particular method. I think in the homework assignments, there were questions asking you to use one of these methods specifically. There was one asking you to use the big formula, although for the sake of time, I'm hoping to not cover the big formula. I don't know for sure if you need to know it or not though, but I'm planning on not covering the big formula because it just takes a little while. And so no, I'm only going to cover methods 1 and 2, but I just wanted you guys to be aware of the big formula as another way of calculating determinant, okay? But I have nothing to say about using the big formula aside from reminding you guys that it exists. So you might need to know it, but I'm not planning on covering it unless you guys ask about it at the end, if I have time for a little bit of Q&A. Right, okay. So I have kind of like two examples set up to kind of illustrate calculating determinants using row and column operations. So to save some time, in this first example that I have prepared, so it was a 4x4 matrix, but to save some time, I've already written out the row operations, okay? Just so we don't have to do it, okay? So let me see what happened in this example. So let's say we want to calculate the determinant of this matrix A, okay? So what I'm going to do is I'm going to kind of keep track of how all the row operations that we performed affected the determinant. Okay? So when I first performed these types of operations, I'm adding a multiple of a row to another row. Remember that those types of operations have no effect on the determinant, okay? So this matrix here will have the same determinant as the determinant of A. Okay? But when I go from here to here, what I did is I multiplied row 3 by -1/3, just because of all the 3's, it looked like something nice to do. But when I multiply a row by a number, the resulting matrix, its determinant, will be scaled by that amount as well. So this matrix, its determinant should be -1/3 times the determinant of A, okay? And then from here to here, what I did was I swapped rows 2 and 3. So in this matrix, its determinant will be the negative of what we have here. So I'm just changing the sign. So it becomes like +1/3 times the determinant of A. And then here, this is adding a multiple of a row to another row. So that won't change the determinant. And then likewise, again, I'm adding a multiple of a row to another row. So again, that doesn't change the determinant. So in this matrix at the end, its determinant should be 1/3 times the determinant of A, okay? Now, on the other hand, though, this is an upper triangular matrix. So the determinant of a triangular matrix should be the product of its diagonal entries. Okay. So here, the determinant of this matrix will be 1 times 1 times 2 times 2. So that'll be 4. So we have 1/3 times the determinant of A equals 4. So therefore, the determinant of A would be equal to 12, okay? So that's like kind of one example of seeing how you can use row or column operations for calculating determinant. Yep, that's right, yeah. So the row swap changed the sign, so that's why it went from -1/3 to +1/3. Okay. Okay. All right, and then I had kind of another example of a different flavor prepared here. Yeah, so I guess like me personally, if it's larger than 3 by 3, I tend to do some row or column operations. Now you could still use cofactor expansion though, but sometimes I think cofactor expansion gets a bit messy when it's 4 by 4 or larger. That's just kind of personal preference. And yeah, it definitely needs to be a square. That's right. Yeah, for 3 by 3, I tend to just do cofactor, right? Because I think it's faster than the elimination typically. Good question. So the reason why it's 12 is because we have 1/3 times the determinant equal to 4. And what I did is I multiplied both sides by 3. Yeah, and that's how we got determinant was equal to, whoops, sorry. That's how we got determinant was equal to 12. Nope, let's see. So let me get the mouse. Yeah, because here it's not that determinant A is 4 times 1/3, but it's 1/3 times the determinant is equal to 4. Okay? All right, cool. Let me see here. So, oh yeah, so let me look at this other example next as well. So we're given the determinant of this 3 by 3 was -3. And we want to calculate the determinant of this thing here, okay? So I guess the idea of this would be that this matrix can be obtained from the original by doing some row and or column operations. So we want to think about like what row or column operations need to be performed to get from this original matrix to this matrix over here, okay? All right. And here it can be a little bit difficult, but let's take a look and see what happens. So the first thing that I kind of notice is when I look at the first column, let me see here. So it looks like the first column has been multiplied by 2, but it also looks like the A and the G were swapped, right? Yeah, so notice the first column was multiplied by 2, but also A and G have been swapped. So I think what I might want to do is multiply the first column by 2. But then because the A and the G are swapped, I believe I need to swap row 1 and row 3 as well. So let's also do row 1 and row 3 swap. So that gets us this new matrix, 2G, H, and I, 2A, B, C, 2D, E, F, right? Okay. Yeah, and so what we have looks pretty good. So then the only difference now is that the third column is different. So, but yeah, someone pointed out, you can see the third column, we're subtracting the second column from the third one is what we're doing. I minus H, F minus C, C minus B. So if we do like column 3 minus column 2, that gets us the matrix that we had in question here. Okay. So then I'll kind of do something similar to what I did before, where I'm going to keep track of what the determinants were at each step. So originally the determinant was -3, but when I multiplied the first column by 2, the determinant of the resultant matrix should now be 2 times -3. So right now the determinant of this matrix is -6, okay? So then what we did is we swapped rows. So when you swap rows, the determinant should change sign. So instead of being -6, once we swap rows, now the determinant of this matrix should be +6. And then adding a multiple of a column to another column does not change the determinant. So the final answer is that the determinant of this matrix should be equal to 6, okay? All right, so any questions about that? That's an interesting question. I think if you did cofactor, and I think you could still get the answer by doing cofactor expansion, but I think it would be rather messy because you're going to be multiplying just a bunch of variables together. Yeah. But if you did do cofactor expansion, I think you would kind of get that this when you work it all out. You would have seen that it was like -2 times this when you worked it all out. But yeah, it would be super messy. So let's see here. If we did swap twice, then it would be -6, right? But we only swapped once, so we did one row swap, which is we swapped row 1 and 3. Okay. Yeah, and subtracting, so like adding or subtracting a multiple of a column to another column does not change anything. That's right. All right, so then, and then like I was saying a little bit earlier, remember that there was this big formula that you could use for calculating the determinant. I'm not going to go into the big formula just because we don't have that much time, but kind of be aware of it in case you do need to know it, okay? And yes, that's correct. Yes. Yeah. So all the stuff that we talked about for column operations is basically the same for row operations and vice versa. Yeah. Okay. So down here, I just have a couple more properties of determinant listed. So some properties, the determinant of A transpose is always equal to the determinant of A. If you have an n by n matrix A and you multiply it by a scalar k, the determinant of that matrix is going to be, k to the n times the determinant of A. So it kind of looks like you can factor a constant outside of the determinant, but when you do that, it gets raised to the n, n depending on the size of A, okay? Maybe the most important and maybe the most interesting property is this one, that determinant of A times B is equal to the determinant of A times the determinant of B. And as a consequence of that, if you want the determinant of A to a power of k, that's going to be equal to the determinant of A raised to that power, okay? So that will be true for k equals 0, 1, 2, etc. 0 is kind of a special case, but when you have a matrix to a power of 0, we consider that equal to the identity matrix, okay? For this class, I think the most important property of determinant, though, was this one here, that a matrix is invertible if and only if its determinant is not equal to 0. Or you could flip that and say that A is not invertible if and only if its determinant is equal to 0. So this was actually kind of the most important result for us in this class, at least for determinants. Okay. Yeah, so on the third property, how I said like if A and B are the same size, that might seem like a strange thing to say, but the reason why I say that is because, so I guess first, if A and B are different sizes, let's see. So let's say A is, well, okay, so first, if A is n by n, you'll notice that B has to be size n by n as well in order for the product to be defined and for the product to be a square matrix. But in theory, you could have a situation where A is a rectangular matrix. So if A is n by k, but let's say that B was k by n. In this case, so when they're different sizes, there would have to be something like this. So the product is square, so you can compute the determinant of the product, but since A and B themselves were rectangular in this case, this side would be undefined. Okay, and then someone is asking, how would you show the matrix is invertible without using the determinant? So like without this property? There's a couple of ways you can do that, but probably the simplest method, with aside from determinant, is you guys remember that to calculate the inverse, one method. One method was to take A and augment it with the identity matrix on the right. And you had to do row operations until you got identity on the left. And then whatever you had on the right would be the inverse. Okay. But for this method to work, your matrix A would have to have a full set of pivots so that you could reduce it to the identity matrix. So you can say that that A would be invertible, like if and only if it had n, I guess, non-zero, to emphasize that part, non-zero pivots. Assuming A is n by n. So that's probably the other way you would check that a matrix is invertible or not, by looking at its pivots. So you'd have to do some row operations to figure out how many pivots it has. Yeah, okay. Okay. And then if your matrix is invertible, then this property 4 that I stated earlier, this property would also hold when k is a negative integer, if A is invertible, okay? So I guess like in particular, the determinant of A inverse itself would be the determinant of A raised to a power of -1. So it would just be the reciprocal, okay? Some other things related to matrix inverse and determinant. There was this formula for calculating the inverse of a matrix in terms of the cofactors of the matrix. Okay. And so I know that there's maybe a 2 or 3 homework questions, I think, that kind of involves this formula. So it says that you can calculate the inverse of a matrix by doing 1 over the determinant of A times C transpose, where C is the matrix of cofactors of A. I didn't want to spend too much time on this, so what I did is I worked out an example already. So here for this matrix A, I did a couple things. So I calculated its determinant by doing expansion along the second row. It turned out to be -1. What I did here is I computed all of the cofactors of A, okay? So let's just take a look at some of these. So for the 1, 1 cofactor, you cross out the first row and the first column. So we had this 2 by 2 remaining. The determinant is AD minus BC, so that's how we got -2. For the 1, 2 cofactor, you go to cross out the first row and the second column. That left us with 1, 3, 1, 0, which we have here. And then you'll notice I put a minus sign in front because for that cofactor, it should have a minus sign in front of it, okay? So you'll notice that these 4 cofactors end up having a minus sign in front of them, okay? So what I did is I just worked out all the cofactors, and then this formula says that this one here, you can get the inverse by doing 1 over the determinant, which ended up being -1. And then it's the transpose of the cofactor matrix. So notice I took the cofactors, but I transposed them. So this first column, I put it into the first row. This second column of cofactors, I put it into the second. Okay, so this second column of cofactors, I put it into the second row because I need to transpose it. Likewise, this third column of cofactors that we had, I transposed it and made it the third row, okay? All right, and like I said, you guys will have access to this later, so you'll be able to take a closer look at the work that I did if you need it. Yeah. And then I'm not so sure how important this is, but I thought maybe I would mention it. So Cramer's rule, I don't know if you guys remember what that was, but when you have an equation ax equals b, where a is invertible, so that 1 over -1, let's see here. So that was 1 over the determinant of a. And I did it earlier. The determinant of a was -1 is what I found, okay? Okay. Okay, so Cramer's rule says that like when you have a system of equations ax equals b, you can solve for the ith component of x, or the ith variable xi, by doing the determinant of ai over the determinant of a, where ai is the matrix obtained by replacing the ith column of a with b. Okay. Well, so I guess the inverse of A is the transpose of the cofactor matrix, and then multiplied by this scalar as well, okay? But yeah, specifically it's the transpose of the cofactor matrix that we have there in the formula. Okay. And I have a little illustration of Cramer's rule down here, okay? So here I just kind of set up a system of equations, ax equals b. So Cramer's rule is saying you solve for x, y, and z just by using this formula. So to see how that works is to solve for x, what you're going to do is you're going to take a and replace the first column of a with b. So notice I replaced the first column of a with 2, 0, 3 down here. I left the remaining columns unchanged. So if you do this 3 over 3 determinant divided by the determinant of a, that will give you the solution for x. I didn't show the work, but if you guys work out the determinants, it's going to be -7 over -1 is what I got. Likewise, to solve for y, using Cramer's rule, you would take a, but replace the second column with b. So that's what I did down here. This is a, except the second column was replaced with b. So if you do this determinant over the determinant of a, that should give you this solution for y. I didn't show the work, but what I got was 9 over -1, so I think it should be -9, okay? Lastly, Cramer's rule says that z should be the determinant of a, except replace the third column of a with b. So that's why we had 2, 0, 3 here, but otherwise it's the same as a. So you do that determinant over the determinant of a. I got that to be 7 over -1, so I got it to be -7 in the end, okay? So you guys can take a look at that later just to kind of confirm everything checked out. Okay. All right, but let's see here. Well, it's I already worked this out prior to the review. So it's not that I worked it out just now super quickly. Yeah. So this is something I actually did prior to the review. But I felt like I had a lot to cover, so I didn't want to spend too much time on everything. So these two examples here, I actually worked them out ahead of time. And you'll be able to see the work. Yeah, that's right, yeah. So here, this is wraps up the material that I had on determinants. So I still have the work about like eigenvalues and eigenvectors to go over. But I think at this point, it's maybe a good idea for us to take a short break. Okay. So let's pause for a moment. We'll take a 5-minute break. So we'll resume around 12:09 or 12:10. Okay. Okay. Right, and yeah, to clarify, it's not that I did the work super quickly, but I did the work ahead of time, rather, is what happened. Just so I wouldn't have to spend the time doing the work during the review. That's right. Yes, that is correct, yeah. All right, so I'll go ahead and wait until 12:10, so a little bit less than a minute, and then I'll resume. So I know that in the email I said that I was hoping to do like a review from 10 to 12, and then maybe like 12 to 1 would be Q&A. But I still have some material to cover, so I think what I'll do is I'll go ahead and finish the material that I have prepared. That might take us until 1 o'clock though. But then I can maybe stay a little bit after 1, maybe not all the way until 2, but I'll maybe stay maybe until like 1:30 perhaps, just to try to answer if you guys have any questions about any other topics. All right, and it's 12:10, so I'm gonna resume. So I just had kind of one more chapter that I wanted to cover, which is everything about the eigenvalues and the eigenvectors. Yeah, so we did stop, so we are closed for the semester for the drop-in tutoring. So me though, it's like all of our student workers are taking finals, so they're not available to work. But I'm not a student here, so that's why I'm able to still work today, yeah. Okay, so we'll talk about eigenvalues and eigenvectors. So kind of like with determinants, this is something that you can only do with a square matrix. So here I just kind of wrote down some definitions. So lambda is an eigenvalue of A if AX is equal to lambda X for some non-zero vector X. Okay. And then X would be called an eigenvector of A corresponding to the eigenvalue lambda. Okay. And sort of like the short story of how to find eigenvalues and eigenvectors is to find the eigenvalues of a matrix, you want to compute the determinant of A minus lambda I. Some people will do lambda I minus A. Either one is fine, okay? So whichever one you prefer. So compute one of those and set it equal to 0. And then you'll solve for lambda by factoring or perhaps some other method if factoring seems difficult, okay? And we'll see that with the example that we have here. To find the eigenvectors, essentially for each eigenvalue lambda, you want to find the null space of A minus lambda I, or again, you could do lambda I minus A, one or the other. But find the null space of A minus lambda I, they call that the eigenspace corresponding to the eigenvalue lambda. Essentially, the eigenvectors would be the non-zero vectors in the eigenspace. Okay. And I'm just going to illustrate all that with the example that I have set up right now. So we're going to find the eigenvalues of this matrix and then the corresponding eigenspaces. So first is getting the eigenvalues. We'll have to do the determinant of A minus lambda I. All right, so for A minus lambda I, all you have to do is minus lambda to each of the diagonal entries of A. So we're going to have 1 minus lambda, 0 minus lambda, 1 minus lambda along the diagonal, just subtracting lambda from each of them. Everything else is going to remain the same. Okay. So we have this 3×3 determinant that we need to compute. So I'll just do the determinant by doing cofactor expansion. Now do cofactor expansion along the first row. That seems like a good choice because it does have a 0 in it. Whoa. Okay, wow, I've never seen that before. Okay, so along the first row, I'm going to take 1 minus lambda times, and then we have this 2 by 2 determinant remaining. Okay. And then for the next entry in the first row, that one's going to come with an extra minus on it. So it'll be minus -1, so I'll do +1. Cross out the row and the column. We have this 2 by 2 remaining. Okay. And then we're going to have a +0, so I don't need to worry about the last one, okay? All right, let's work out these 2 by 2 determinants next. So here, remember, it's a d minus b, c. So a times d is going to be negative lambda plus lambda squared. We're going to have minus +1. Okay. And then let's see what we have here. -1 times 1 minus lambda. So -1 times 1 minus lambda. Okay. And so that was a times d, and the bc was 0. So that's why it's just a times d. Okay. Now here I noticed that we have a 1 minus lambda in both of these terms. So I'm going to factor the 1 minus lambda out from everything. If I factor out the 1 minus lambda, that leaves us with negative lambda plus lambda squared minus 1. And then we have an extra -1 when we factor this 1 minus lambda out. Okay. So let me see, so that's 1 minus lambda times lambda squared minus lambda minus 2. So then if I continue factoring the quadratic, that should factor as lambda minus 2 times lambda plus 1, okay? All right. So then the eigenvalues are where this is equal to 0. Okay. So then for the product to be equal to 0, lambda has to be equal to +1 to make this one a 0, or 2, or -1. Okay? So it looks like those were our 3 eigenvalues. Okay. So now we have to find the eigenspace corresponding to each eigenvalue. So the eigenspace is the null space of A minus lambda I. Let's just start with lambda equals 1 first. So I need to look at A minus lambda I, this time when lambda is 1. So this is what A minus lambda I looks like over here. So I'm just going to plug in 1 for lambda. That's going to give me 0, -1, 0 on the diagonal. Okay. And then what we want to do is we want to find the null space of this matrix, okay? So to find null space, I did a little example earlier, but you want to do some row operations, do some elimination. How much elimination, how many like row operations you do, it's a little bit up to you. I mean, I think if I were to do something on this example, I would maybe I see lots of minus signs everywhere, so this isn't super important, but I think I would maybe just multiply all the rows by a negative, because it looks much nicer to have positive numbers everywhere. And then maybe I would like swap row 2 and row 1. Just to get like a pivot up here in this first position. And then we'd have so the first column is kind of already taken care of, incidentally. We have the second pivot here. If I want the reduced row echelon form, I could do row 1 minus row 2 to eliminate this entry above my next pivot. Likewise, I could do row 3 minus row 2. Now you don't have to get it into the reduced row echelon form like I'm doing right now. Okay. So you could have stopped at somewhere else. It doesn't make that much of a difference. But at some point, once you've done enough of the elimination, at least what I do is I convert this into a system of equations now. So the first row gives me the equation 1x plus 0y plus 1z. We set it equal to 0 because we're looking for the null space. Then the second row will just give me 1y, and again I set it equal to 0, okay? All right. So in my reduced matrix, the third column is missing a pivot, so I'm going to choose z to be the free variable. And again, people will do this slightly differently, but what I tend to do is I tend to parameterize the free variable. So I'm going to set z equal to t. Now here we have that y is equal to 0. And then if z is equal to t, then x is going to be equal to negative t. Okay. So this is what we find for the null space. It's all multiples of the vector negative 1, 0, 1. So then this would have been like the eigenspace corresponding to lambda equals 1, okay? And then this one vector that we have, negative 1, 0, 1, would have been like a basis for the eigenspace. Okay. All right. Now we have to do the same thing for the other eigenvalues as well. So let's take a look at the eigenvalue lambda equals 2 that we found next. So this time we'll need to look at a minus 2i. Okay, there you go. Yeah, so the eigenspace, I guess to be like super precise, the eigenspace itself is all multiples of this vector. You can maybe say it is the span of that one vector. Okay. Okay. So all multiples of that vector. But most of the times in most applications, we only need a basis for the eigenspace. So they often will only care, or they'll often be satisfied, I think, if you just specify the basis for the eigenspace. Oh yeah, and I'm just abbreviating because it's I have to say a right eigenvalue, eigenvector, eigenspace all the time. So it's convenient to have an abbreviation like that, yeah. Okay, so for lambda equals 2, doing a minus 2i. Okay, so I wrote down what a minus lambda I was earlier. So for a minus 2i, if we just plug in 2 for lambda, that's going to give us -1, -2, -1 on the diagonal. Okay. And then again, we need to find the null space of this matrix now. So we'll do a little bit of elimination. This time, I think what I'll do is maybe I will multiply row 1 by negative, just because as a personal preference, I like having +1 as a pivot. Then I think I would do row 2 plus row 1. So that gets us the 1, 0, 0 in the first column. Okay. And then here, if we do row 3 minus row 2, that will eliminate the third row. And here it's not a big deal, but let's maybe multiply row 2 by -1 after that, just because I like positive numbers more. So this would be an okay place to stop. If you want it reduced row echelon form, you could do row 1 minus row 2 to eliminate the 1 that's above this pivot. But again, it's not super important that you do this, but I know some people like to do it, so I'll go ahead and do it. Okay. And so then here, this would be the reduced row echelon form. So then at this point, I'll kind of do what I did over here again. This time, the first row gets us an equation x minus z is 0. And the second equation is y plus z equals 0, okay? Let's try that again. Okay. All right, and then again, the third column happens to be missing a pivot. So therefore, I will again choose z to be the free variable. So let's see, if I set z to be equal to t, then y would be negative t, and x would be positive t. Okay. So the eigenspace is going to be all the multiples of the vector 1, -1, and 1. So you can say the eigenspace is the span of this one vector. And you can say this one vector itself would be a basis for the corresponding eigenspace, okay? So we're kind of almost done. I just need to do the same thing with lambda equals -1 though. So you have to do this for each of the eigenvalues that you find. So I'm going to look at a minus lambda I once again, with lambda being -1. So I'll just plug -1 into this matrix for lambda. So we're going to do minus the -1 to +1 along the diagonal. So it'll be 2, 1, 2 on the diagonal. And everything else was the same. Okay. All right, and then again, we need the null space of this matrix, so I'll do some elimination. So I'll maybe start by swapping row 1 and row 2. And this isn't super important, but maybe I'll multiply row 1 by -1. Again, it's more of a personal preference. I like having +1 as a pivot. Let's do row 2 minus 2 row 1. And if we did that, it's going to be like -1 plus 2 and 0 minus 2. Okay. So we can do row 3 plus row 2. That will eliminate the third row. I think I may as well do row 1 plus row 2. It's pretty simple to do. That will eliminate this -1. And then row 1 plus row 2 will make this a -1. And then that gets us the reduced row echelon form. I'll write out the corresponding system of equations. Okay. And I guess again, the third column is the one that's missing a pivot. So again, I'll choose Z to be free. So if I set Z to be T once again, Y will be 2T, X will be T. So the eigenspace is all of the multiples of the vector 1, 2, 1. And then 1, 2, 1 itself gives us a basis for the eigenspace. Okay. So then that gets us all the eigenvalues and the corresponding eigenspaces for this matrix that we had, okay? Now let me kind of record the information real quick. So for lambda equals 1, we found -1, 0, 1 as a basis for the eigenspace. For lambda equals 2, we found 1 minus 1, 1 as a basis for the eigenspace. And for lambda equals -1, we found 1, 2, 1 as a basis for the eigenspace. Okay. All right, were there any questions about that before I move on? It does, yes, and we'll see that later, that's right. Okay. It is as well, that's right. So you guys have maybe guessed what I'm gonna be doing, but I'm actually gonna like use this example in the later parts as well, because as you can tell, this takes a long time to do. So if I had to create a new matrix for each concept that I want to illustrate, it would make the review way too long. So yeah, I'm going to be using this example to illustrate some of the other theorems and facts related to eigenvalues and eigenvectors, and some of the other examples. Okay, so let's go ahead and move on to what do I have next? Okay, so I guess this page is somewhat of like a miscellaneous section, if you will. I'm just covering some sort of random facts about eigenvalues and eigenvectors, and facts that seemed maybe somewhat relevant to some of the questions that were in some of your assignments. So the first couple of facts that I have stated here are about the trace and the determinant of a matrix and how they relate to the eigenvalues. So first, for those of you who don't know, the trace of a matrix is defined to be the sum of its diagonal entries. And then there's a theorem that says that the trace of A also happens to equal the sum of the eigenvalues of A, okay? And then the determinant, which we've learned about just now, it turns out that the determinant happens to equal the product of the eigenvalues of A, okay? That's a good question. So actually, no. So a matrix does not have to be in upper triangular form for the trace. So for instance, for the matrix that I have right now, you can compute its trace readily. It would be -1 plus -3 plus 10. That would be the trace of this matrix here. Whoops. So yeah, just add the diagonal entries, and that gives you the trace, okay? All right. And yeah, so I do have an example to try to utilize these two facts. So let's take a look at what we have in the example right now. I have this matrix A, and there's kind of two parts to the question, I suppose. So first is show that the vector -2, 0, 1 is an eigenvector of A. And then next is use the trace and the determinant to find the remaining eigenvalues. So to see how to do that, let's just look at this first part, which is showing that -2, 0, 1 was an eigenvector of this matrix. Okay. I think I probably need a bit more space, so I'm going to move this down. Okay. All right, so to show that -2, 0, 1 is an eigenvector, what I would not do is I would not compute the determinant of A minus lambda I to get the eigenvalues, and then I would not do all of this, if you will, okay? So there's something much simpler that I think you should be doing instead to show that -2, 0, 1 is an eigenvector, which is if you go back to the original definition of eigenvalues and eigenvectors, eigenvalues and eigenvectors, they satisfy this equation, ax equals lambda x. So what I'm just going to do is I'm just going to take A and multiply it with the vector -2, 0, 1. Okay. And let's see what the product looks like right now. So it's going to give us +2 plus 0 minus 6. So that should be -4 altogether. Okay. Next, we're going to get +8 plus 0 minus 8, which is 0. And then you're going to get -8 plus 0 plus 10. Okay. Now, if negative 2, 0, 1 was an eigenvector, then A times negative 2, 0, 1 should result in a scalar multiple of itself. And when I look at this result that we have negative 4, 0, 2, I notice it is 2 times the original negative 2, 0, 1 that we multiplied by, okay? So here what we see is like A times this vector gave us a scalar 2 times the same vector. So this proves that negative 2, 0, 1 is an eigenvector of A. And we also see that lambda equals 2 was the corresponding eigenvalue. Okay, and then let's see here. Yeah, go ahead and ask your question.
Can you hear me?
Oh yeah, I can hear you, yeah.
Okay. So earlier when you were doing uh when you said like it was the basis of and then you found like an eigenvector, I think. Is that like what that would be the x here, right?
Yeah, that's right, yeah.
Okay, okay. Just going backwards. Okay.
Yep, that's fine, yeah. Is anyone else? Yeah. Okay, looks like he's gonna try and refresh. All right. Yeah, let me know if there is like an issue at some point. Yeah. All right. Oh
Thank you.
wow, I see. Yeah, no problem, no problem. Okay. So I guess like right now what we've done is we've answered part A. We showed that this was an eigenvector, and we also find the corresponding eigenvalue. There is a second part to the problem which says to find the remaining eigenvalues by using the trace and the determinant. So let's try to see how we would do that. Okay. Oh, if you see it black out like that, it means I accidentally minimized my OneNote. So if I minimize it accidentally, it does black out like that, if that's what you were referring to. Yeah. So when I do that, I'm like, crap, because I can see that I did it. Yeah. Okay. So first, let's compute the trace and the determinant of A. And we kind of already did the trace earlier. So let's do the determinant of A next. So to do the determinant of A, let's just do cofactor expansion. It doesn't really matter. I'll do it along the first row, okay? So determinant will be starting with -1 times this 2 by 2. I think I'm just gonna scooch everything down a bit more. Come on. Oops. Yeah, you want to do the trace of the original matrix, yeah. Because when you do row operations, that will have an effect on the trace. in general. Yeah, okay. Ooh, good question. Yeah, so just real quickly, yes, we are recording this right now. And yeah, I will be uploading the recording later today to our YouTube channel. The link was, I posted it here. Let me copy. Yeah, there you go. Perfect. All right. That's true. Yeah, and your comments won't be shown. Okay. Sure. Okay. All right. So yeah, let's continue with what we were doing here. So right now, I was going to compute the determinant of A because we're supposed to use it somehow to get the remaining eigenvalues. Okay. So I'm doing cofactor expansion along the first row. So -1 times this 2 by 2. Next would be, we have the -4, but then this cofactor comes with an extra minus, so I'll make it a plus. And then I cross out the row and the column, and we have this 2 by 2 remaining. And then lastly, I'm going to have -6. I cross out that row and that column. Here's the 2 by 2 that we have remaining. And let's just compute the 2 by 2 determinants now. So we have -30 minus a -40. So that should be +10 there, okay? This one's going to be -40 minus a -32. So -40 plus 32 is -8. And then at the end for this one, we have -20 minus a negative, so plus 12. So we -8, okay? Let's compute this. So -10 minus 32, but plus 48. I think that leaves us with the determinant being equal to 6, okay? All right. So now let's see. So we know that the trace of A, the sum of the diagonal entries was 6, okay? And then, well, we also know those that the trace should be equal to the sum of the eigenvalues of A, all right? So as a 3 by 3 matrix, it should have 3 eigenvalues. One of them is 2. And then there's 2 remaining eigenvalues, which we need to try and find using the trace and the determinant, okay? So I'm calling the other 2 eigenvalues of A lambda1 and lambda2. Okay. And then here 2 comes from this eigenvalue that we found earlier. Okay. So the sum of the eigenvalues equals the trace. Likewise, the product of the 3 eigenvalues should equal the determinant, which I guess by coincidence was 6 as well. Okay. So let me see what that leaves us with. Yeah, so for an n by n matrix, so we'll always have n eigenvalues. Now they won't necessarily be distinct though. So sometimes like an eigenvalue will be like repeated, and we'll see an example of that later. But yeah, so altogether I have n eigenvalues, but some of them might be repeated though, okay? Okay, so what I've done right now is I just took the sum of the eigenvalues, set it equal to the trace, took the product of the eigenvalues, set it equal to the determinant, which happened to be 6 as well. And I guess the idea here would be we want to see if we can solve for lambda 1 and lambda 2 from all of this. Yeah, so trace is the sum of the diagonal entries, and determinant is what we did here. Now, if the matrix was a triangular matrix, then its determinant would be the product of the diagonal entries. But that's only if the matrix were triangular. Could you do that for the determinant? Unless you could also compute determinant by doing row operations and reducing to upper triangular. That's right. Yeah, that's right. Okay. And so I guess, yeah, at this point, what I have in mind is we have like a system of equations, so we could try to solve for lambda 1 and lambda 2 from these two equations, all right? So let me rearrange the equations a bit. So for this equation, let me move the 2 to the other side. So that's like lambda 1 plus lambda 2 should be equal to 6 minus 2 would give us a 4. This equation, let's divide both sides by 2. So it gives us lambda 1 times lambda 2 has to be equal to positive 3. So that was that the determinant equals the product of the eigenvalues. When you multiply the diagonal entries of a matrix, if your matrix is triangular, it gives you the determinant. Otherwise, I'm not sure if it's anything special if your matrix is not triangular. Yeah, if it's triangular, the product equals the product of the diagonal entries would be the determinant. Yeah, 6 divided by 2 is how we got the positive 3. Yep. Okay, and then let's see what we can do here. I guess maybe I would solve for one variable in one equation and then multiply it to the other one. Let's say we take this equation. Let's say lambda 1 should be 4 minus lambda 2. So I'm going to plug that into this equation. So we have lambda 1, which is 4 minus lambda 2, times lambda 2. Lambda 1 times lambda 2 should be equal to 3, okay? So 4 lambda 2 minus lambda 2 squared equals 3. So I distribute it. Let's move everything to one side of the equation. I'm going to move everything to the right-hand side. Okay, I see. So then here, I guess we can factor it, right? So lambda 2 minus 3, lambda 2 minus 1. Okay. So right now it's kind of giving, it seems to be giving two possibilities for lambda 2. if we go back and solve for lambda 1 using, I guess we could use this actually, right? So we had lambda 1 is 4 minus lambda 2. So what happens is you see that if lambda 2 equals 1, you're going to get lambda 1 is 3. But if lambda 2 were 3, then that would give you lambda 1 is 4 minus 3 then, so lambda 1 would be 1. So essentially what this is telling us is that the other two eigenvalues are going to be 1 and 3. So altogether, you can see the eigenvalues of A are 2, which we found from part A. And then the other two are going to be 1 and 3. Okay? You might be able to guess lambda 1 and lambda 2 just from these equations, but in the event that you're able to guess them, like maybe you just guessed 1 and 3 and it worked, right? I guess you could have done that for sure. But I guess like systematically, you would maybe solve it like this, so okay? But yeah, if you just see the answer right away, I guess just, say by inspection, this is the answer. I think that would be fine, yeah. All right. All right, cool. So let's see here. I have a little bit more I want to talk about. All right. So here I listed some more properties of eigenvalues and eigenvectors. So this third property that I have here, so if lambda is an eigenvalue of A, and then if X is a corresponding eigenvector, then lambda plus K is going to be an eigenvalue of A plus Ki, and then X would be a corresponding eigenvector. If you're looking at like the eigenvalues of A to the K, lambda to the K will be an eigenvalue of A to the K, and then X would be a corresponding eigenvector. And then you can sort of generalize these two properties into this one down here. It's a little bit awkward to state, so this is kind of how I stated it. So let's say that if you have like a polynomial, so here I have like P of t is like an t to the n and so forth. I define this like sort of polynomial matrix, I guess. So it kind of looks like you're just plugging in A into the polynomial. At the end, you have to tack on an identity so that you can like add the matrices together. Okay. So this P of A is going to be a matrix. You plug in A, if you multiply and add everything up, the result will be like some matrix, okay? And what I wanted to say was for such a matrix, if lambda is an eigenvalue of A, then P of lambda would be an eigenvalue of P of A. And then again, X would have been like a corresponding eigenvector, okay? So if that maybe doesn't make too much sense, I can try to illustrate what I mean with this example here, okay? Okay. So in this example, we're given that the eigenvalues of A are -2, 0, 1, and 3. And then we're asked to find the eigenvalues of this matrix here, okay? So I guess like associated with this matrix is like a polynomial. In this case, the associated polynomial will be like t squared minus 2t plus 5. So then the eigenvalues of this matrix are going to be P of -2, P of 0, P of 1, and P of 3. Okay. So what I'm going to do is I'm going to take the eigenvalues of A and just plug them into this polynomial that we had. That is correct, yeah. For the identity matrix, an n by n identity matrix will have n eigenvalues, but all of those eigenvalues would be equal to 1. Right. Yeah, but here what I'm going to do is just plug the eigenvalues into the polynomial. So it'd be like -2 squared minus 2 times plug in -2 for t plus 5. Plug in 0 for t. Looks like it's 5 again. Okay. Plug in 1 for t. You'll get 1 minus 2 plus 5. Then plug in 3 for t. Okay, 8. So then the eigenvalues of this matrix would be like 5, 5, 4, and 8. Okay. So that's what I was trying to say with this property here, if you will. Okay. Any questions about that? Okay. P of -2. Did I mess that one up? Yes, I did. Yeah, thank you. I thought it was 4 minus 4, but yeah, it looks like it's +4 plus another 4, so it's 8 plus 5. So yeah, it looks like it should have been 13. Thank you. Okay. So then this is one more fact which I have here. Basically, just eigenvectors that correspond to distinct eigenvalues are going to be linearly independent. Okay. I don't have any examples involving that, but it's just a fact that I think you should know. So let's continue. So I'll talk about diagonalization next. Oh, I already wrote them down. Okay. Well, so real quickly for diagonalization, if A is an n by n matrix, so A is going to be diagonalizable if and only if it has n linearly independent eigenvectors. That's a good question. You just have to try to cram it all in by tomorrow, right? Right, right. Okay. Okay. So a matrix is diagonalizable if and only if it has, or for an n by n matrix, it is diagonalizable if and only if it has n linearly independent eigenvectors. So if, let's say that your matrix has eigenvalues lambda 1 through lambda n, and let's say x1 through xn are a corresponding set of linearly independent eigenvectors. Okay. If you take the eigenvalues and you put them into the diagonal of a diagonal matrix, and then if you take the corresponding eigenvectors and you put them into a matrix as columns, so like x1 being the first column and so forth, then you get this factorization of A. The A is x times this is a capital lambda times x inverse. Okay. The fact that x is invertible comes from the fact that the eigenvectors are linearly independent. Okay. And when a matrix can be factored like this, that's what it means to be diagonalizable. Okay. We'll see. Yeah, we'll talk about that. Okay. So actually, let me. Well, okay, sure. You're thinking of something else, which I'll get to in the next part, I think. Right. So I guess the issue is let me go back to. So we had this example from earlier where we found its eigenvalues along with a corresponding like eigenvector. Okay. So let me jump to that real quickly just to answer one of the questions that was posted. It was this one here. Okay. So let me take a look at the work that we did. So when lambda was, just as an example here, when lambda was equal to 1, okay, we found the eigenspace was all multiples of the vector negative 1, 0, 1. So that means like, negative 1, 0, 1 is an eigenvector corresponding to the eigenvalue of 1. But so is negative 2, 0, 2. That's also an eigenvector corresponding to lambda equals 1. Any multiple of this vector is going to be another eigenvector for this eigenvalue. But these eigenvectors are not linearly independent though, right? Because they are multiples of each other. Yeah, so like eigenvectors can be linearly dependent, particularly when they correspond to the same eigenvalue. That's kind of like the issue, if you will, okay? Okay, all right. But if your matrix has, so one of the things that we did mention just now though was that if that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So therefore, if your n by n matrix has n distinct eigenvalues, then it will definitely have n linearly independent eigenvectors. So it will definitely be diagonalizable. So the issue is if your matrix has fewer than n distinct eigenvalues, meaning that some of them were repeated, then there's a potential that it might not be diagonalizable, okay? So if it has a fewer than n distinct eigenvalues, because some of them are repeated, then it may or may not be diagonalizable. Okay. I'll include a link in the YouTube video description once I upload the recording. I'll probably also send out an email though as well with like a link to the YouTube recording, and then I can also include a link to the OneNote in that email as well. Okay. Okay. So here, because this matrix, this 3×3 matrix had 3 distinct eigenvalues, we know that these eigenvectors are going to be linearly independent. Okay, we'll see an example of that in the next section, actually. So we'll see. Okay, but so if we wanted to diagonalize, okay, so first A is diagonalizable. Since it has 3 linearly independent eigenvectors. Okay. And then if you want to actually diagonalize the matrix A, okay, essentially what you would need to do is, okay, so you would take the eigenvalues and put them into a diagonal matrix. And then you would take the eigenvectors and put them into a matrix as columns. Now here, be consistent with the ordering. So if I choose -1 to be the first diagonal entry, I should choose the eigenvector corresponding to -1 to be the first column in X. Okay. Likewise, since I put lambda equals 1 as the second entry in the diagonal matrix, I need to take the eigenvector and make it the second column of this matrix. Okay. So be sure that the ordering of the eigenvalues and eigenvectors is consistent. Okay. Aside from that, the order wouldn't matter. So for instance, you could do like 2, 1, -1 for the eigenvalues. You would just have to take 1, -1, 1, and make that the first column, because that was the eigenvector corresponding to lambda equals 2. And then likewise, 1, 2, 1, you would now put it in the third column, since it's the one that corresponds to the -1. Okay? So the order doesn't matter as long as you are consistent, though, with the ordering between these two. So then with those matrices, you could factor A as the product X times the capital lambda matrix, and then times the inverse of X. Okay. And I don't think that they really want you to calculate the inverse. I think you can just write it like that. Okay. I'm pretty sure that's the case at least. But if you want to be extra certain, you can ask your professor just to double check. But I think they wouldn't really care for you to calculate the inverse for questions like this. Okay. And then one of the important applications of diagonalizability is that it makes it easy to compute high powers of a matrix. So here, if you can factor A like this, if it's diagonalizable, you can calculate A to the K by simply raising this diagonal matrix to the K and then multiplying by X and X inverse. So for instance, if you want to compute like A to a power of 20, okay, so A to the 20 in theory means A multiplied with itself 20 times. And if you think about how complicated matrix multiplication is, you can maybe imagine that would be quite a bit of work to multiply A by itself 20 times. But if your matrix is diagonalizable, then if you diagonalize it, you can just raise the diagonal matrix to that power, which would just apply to each of the diagonal entries. And then the idea is that this would be something that's much simpler to compute as opposed to multiplying A by itself like 20 times, if you will, okay? So that's kind of like one little application of diagonalization. Okay. So a brief summary though, to diagonalize a matrix, you need to get the eigenvalues, you need to get the corresponding eigenvectors, put the eigenvalues into a diagonal matrix, and then put the eigenvectors into a matrix as columns, and then you have this sort of factorization of A, okay? Okay. And then I guess we're kind of almost done. So symmetric matrices have some like very special properties when it comes to their eigenvalues and their eigenvectors, okay? I've listed some of the properties here. So one of the properties is that the eigenvalues of a symmetric matrix are always real. We haven't seen an example, but sometimes when you're calculating the eigen values of a matrix, I can just make one up real quickly, actually. So just hypothetical, let's consider this matrix. Okay. If you want to find the eigenvalues of this matrix, so let's say we're going to do A minus lambda I. So we would minus lambda along the diagonal. And then if we compute this 2 by 2 determinant, it's AD minus BC. So it's going to be minus a negative 1. And when you set this equal to 0, you would get the eigenvalues are plus or minus the, well, so you'll get lambda squared equals negative 1. So lambda would be plus or minus the square root of negative 1, which leads to like imaginary eigenvalues, okay? And I guess in as much as we don't work with imaginary or complex numbers in this class, that would kind of be like a bad thing if that happened. So for symmetric matrices, they're nice because their eigenvalues are always going to be real numbers, so you'll never have like imaginary numbers in the eigenvalues of a symmetric matrix, okay? So that's one property that's good to know, I think. Now, another important property is that the eigenvectors corresponding to distinct eigenvalues, we said before that they should be linearly independent, but for symmetric matrices, there's something stronger that holds, which is that eigenvectors corresponding to distinct eigenvalues are actually going to be orthogonal to each other. So not only linearly independent, but in fact orthogonal, okay? Now this is only true for symmetric matrices though, so keep that in mind. Probably the most important thing about symmetric matrices though is that they turn out to always be diagonalizable, okay? So for any n by n symmetric matrix, you'll always be able to find n linearly independent eigenvectors. And in fact, you can do better than that for a symmetric matrix. You'll always be able to find n orthonormal eigenvectors, so not just linearly independent, but orthonormal, okay? So in terms of like, what does this mean about the diagonalization of a symmetric matrix? Let's say that lambda 1 through lambda n were the eigenvalues. And let's say that q1 to qn is a corresponding set of orthonormal eigenvectors, okay? So you can still do what we did before, pick the values and put them into a diagonal matrix. And you can take the eigenvectors and put them into a matrix as columns as well. And you would have like A equals, Q times capital lambda times Q inverse, just as before. But something special happens when the columns of a matrix are orthonormal, as they would be in this case. So a matrix whose columns are orthonormal is called an orthogonal matrix, and they happen to satisfy this property that the transpose is equal to the inverse, okay? So then this factorization, since Q inverse will be equal to Q transpose, you can actually write it like this. And then this factorization of a symmetric matrix, they call it the spectral decomposition, okay? So it's basically the same as diagonalization, except you have to use the orthonormal eigenvectors for the spectral decomposition, okay? Yeah, so you could still do A equals like X lambda X inverse for symmetric matrices, but you can do something like even more special than that, I guess, which is this spectral decomposition, okay? So then I think maybe some of you might have noticed that this example that I was using earlier, this matrix A is a symmetric matrix. So we found the eigenvalues, they were real as they should have been, according to this fact here. And someone noted that the eigenvectors are actually orthogonal to each other. So the fact that they're orthogonal to each other would actually be a consequence of corresponding to distinct eigenvalues of a symmetric matrix, okay? Okay, so eigenvectors that correspond to distinct eigenvalues of a symmetric matrix should always be orthogonal. So that's why these three happen to be orthogonal, okay? And again, if you, as a reminder, you can check that they're orthogonal because all the dot products are 0. So I'm not going to write it out, but you guys can double check that, okay? So let's say for this matrix A, if I want to find the spectral decomposition, or let's say that, I think in your assignments, you usually had instructions to say like orthogonally diagonalize A. To me, that's basically synonymous with asking you to find the spectral decomposition. Okay. So what you would need to do is get the eigenvalues and the eigenvectors. Fortunately, we already have them because we did the work earlier. Now, however, as I was saying, for spectral decomposition, you must be using orthonormal eigenvectors for it. And right now, the eigenvectors we have are orthogonal, but they're not orthonormal just yet. Okay. So what we're going to have to do is we're going to have to normalize the eigenvectors that we found. So if you guys remember how this works, We just have to divide each of these vectors by their magnitude. So for this vector, its magnitude would be square root of 1 squared plus 2 squared plus 1 squared. Should be square root of 6. If we take the second eigenvector, its magnitude is the square root of 1 squared plus 0 squared plus 1 squared, so that's square root of 2. And then Q3 is going to be 1 over the square root of 1 squared plus 1 squared plus 1 squared, so square root of 3. Okay. So now these will give you a set of orthonormal eigenvectors. So then for the spectral decomposition, just take these eigenvectors and put them into a matrix as columns. So this is Q1. Here's a Q2. Here's Q3. That's Q. If we do times capital lambda, which is the eigenvalues along the diagonal, and then for the spectral decomposition, it's times Q transpose. So here we can actually just transpose Q, so take the columns but write them as rows now. Then this product here will be equal to matrix A, and this factorization would be its spectral decomposition, okay? Well, yeah, so I have one more section. The review is running a bit long, but I will go ahead and cover my last section after this as well. But I probably will not be doing Q&A since it has been pretty long, okay? All right. Let's see, so that's example of spectral decomposition. Now I wanted to kind of summarize, maybe highlight a couple of things about this. I will cover chapters 4, 5, and 6, which were the chapters that were going to be like emphasized for the final. But the final is cumulative though, so it actually covers the earlier chapters as well, okay? I don't know, you'd have to ask your professors, okay? All right. So I wanted to make just a few more notes about spectral decomposition. So if the eigenvalues are all distinct, then the eigenvectors that you find will already be orthogonal. So you'll just need to normalize them to make them orthonormal, okay? That's essentially what we had to do in this example just now. The vectors were already orthogonal, so we just had to normalize them to make them orthonormal. Okay. I see. Now, if you have a repeated eigenvalue, that will lead to a possible complication when you're finding the spectral decomposition, and that you may need to perform Gram-Schmidt on the basis of the corresponding eigenspace to get like orthogonal eigenvectors, okay? So I'll kind of show you how that works with this example here. So let's find the eigenvalues of this matrix right now. So I'm not going to work through this entire example because I see that's getting pretty late, but I'll at least show you what I wanted to show you in this example, okay? So first, let's look at the eigenvalues. So we're going to do the determinant of A minus lambda I. So that's going to introduce a minus lambda along the diagonal. So let me work out what this determinant is real quick. I'll just do expansion along the first row. So I'm going to have negative lambda times, cross out the row and the column. We have this 2 by 2 remaining. Next, we have 1, and this cofactor comes with an extra minus, so that's why it's minus 1. Cross out the row and the column. And then at the end, we're going to have plus 1. And then we're going to have cross out the row and the column. And we have this 2 by 2. Yep. I'm going to multiply these, or compute these 2 by 2 determinants. So this will be lambda squared minus 1. Here we have minus lambda minus 1. And here we have 1 plus lambda is what we're going to get there, okay? Okay, so let's see what we can do. I noticed that on this term, if I factor the negative out of the parentheses, it'll become plus lambda plus 1. So we can actually add the two of these together. So we'll have 2 lambda plus 1s once we combine them. And on the other hand, the lambda squared minus 1, lambda squared minus 1, we can factor it as lambda minus 1 times lambda plus 1, okay? So I can factor lambda plus 1 out from both terms. That leaves us with minus lambda times lambda minus 1 plus 2. And then inside the brackets right now, we have like negative lambda squared plus lambda plus 2, okay? So what I'm going to do here, just because sort of as a personal preference, I'm going to factor a minus sign out of the brackets. The reason why I'm doing that is just so I have a positive coefficient for the lambda squared. Okay. So since I factor out the minus out of the brackets, I have to change the sign of everything on the inside. And then here, if we continue factoring this, this will factor as lambda minus 2 times lambda plus 1, okay? So when we set this equal to 0 to find the eigenvalues, the eigenvalues are going to be negative 1, positive 2, and you see that negative 1 is actually going to be a repeated eigenvalue. So this is kind of, I think this is the first example in this review at least where we have this happening. So we have a repeated eigenvalue. And right now, I'm just going to look at the eigenspace for lambda equals negative 1, okay? So I'm not going to go through the whole problem of finding the spectral decomposition, but let's at least look at the eigenspace for lambda equals negative 1. Okay. So I have to look at the null space of A minus lambda I. So I'm going to plug in -1 for lambda up here. Oh, well, okay, so that's going to be all ones. Okay. So then we need to find the null space. So you would maybe do some elimination. This one's pretty simple though. Just row 2 minus row 1, row 3 minus row 1. Okay. All right. So let's take a look and see what's happening. I've reduced all the way to reduced row echelon form actually. So if you remember, what I normally do at this point is I will convert it to a system of equations. Okay. Now in this case, both the second and the third column are missing a pivot. So that means we have two free variables. In this case, I would choose y and z to be the free variables, okay? So since y and z are both free, I'm going to introduce two parameters. So I'll say like y is equal to s, I'll say z is equal to t. Okay. From there, we could solve for x as being minus s minus t. And I'm going to rewrite this now as a linear combination. So let's see here. I have x should be equal to minus 1s and minus 1t. Y should be 1s plus 0t. And z should be 0s plus 1t. Okay. And another way you can figure out how to get these vectors is just look at the coefficients of s for this one, and just get the coefficients of t for this one, okay? But what's happening in this example is we have two linearly independent eigenvectors. For the eigenvalue of -1. Let's call them v1 and v2. Now, if we were looking for the spectral decomposition, then as we know, we need to be using an orthonormal set of eigenvectors. So first, we would need to make sure that our eigenvectors are orthogonal, and then we could just normalize them to make them orthonormal, okay? The problem that we have right now, though, is that v1 and v2 are actually not orthogonal at the moment. If you check the dot product, it is not 0. So when you have a situation like this, what you would need to do is you would need to take these vectors and perform Gram-Schmidt on them to get like an orthogonal set of eigenvectors. It's not going to take super long, so I'm just going to do it real quick, okay? So if you remember Gram-Schmidt W1, the first vector is just V1. W2, the second vector from Gram-Schmidt is V2 minus its projection onto W1. Okay. I'm just going to do the dot product real quickly. So W1 dot product with V2. It's going to be positive 1. W1 dot product with itself. It's going to be 2. So just going to wrap this up with this computation. So minus 1 will be plus a half. So minus a half. 0 minus a half. And 1 minus a half is 1/2. Okay. Okay, so instead of using the V1 and V2 that we found over here, we could use these vectors that we've got from Gram-Schmidt, because these vectors are orthogonal and we need them to be orthogonal for the spectral decomposition. So then here now we have orthogonal eigenvectors. For the repeated eigenvalue of -1 that we had. Okay, yeah, let's check. So V2 minus 1/2 of W1. Well, so I guess you do get 0 from that, but then you're subtracting from this one as well. But I guess it would be 1 minus 0, so I think it would be 1, right? It's maybe what you guys meant. Okay, I see, yeah. Okay, all right. Thank you. Okay, yeah, so here that gets you to a set of orthogonal eigenvectors. If you prefer, I guess what I would like personally do, but I guess this isn't entirely necessary, but in as much as I try to avoid fractions when I can, one thing you could do is if you just scale this vector by 2, so scaling it by 2 will give you a new set of orthogonal eigenvectors, but maybe slightly nicer because you don't have fractions anymore, okay? Now, ultimately, for the spectral decomposition, you do need to normalize them. So I guess in the end, when you normalize them, you're going to get that fraction with the square root typically in the front. And here the magnitude is 1 squared plus 1 squared plus 2 squared, so it'll be 6. So I just wanted to show you kind of a little complication that might happen for spectral decomposition if you have a repeated eigenvalue, that you might need to do just a little bit of Gram-Schmidt to make sure that you're going to have orthonormal eigenvectors at the end, okay? So this gave us Q1 and Q2. You would find Q3 by looking at the other eigenvalue, lambda equals 2. But I'm going to end the example at this point. Because I know it's getting late, and I'm sure you guys don't want to be here all day, okay? But you would find Q3 by looking at the other eigenvalue, and then you would get the spectral decomposition once you had Q3 as well, okay? All right. Just kind of try to, real quickly, go over the last material that I have, talking about positive and negative semi-definite ness. So here we're only going to talk about these in the context of symmetric matrices. So if A is symmetric, we'll say it's positive definite if all of its eigenvalues are positive. Positive semi-definite if they're all greater than or equal to 0. Similar for negative definite and negative semi-definite, okay? A matrix could be none of the above if it has like both positive and negative eigenvalues. Some people will say that the matrix is indefinite if it is none of these 4, but I don't think this is like universal though, so I don't know if I would necessarily use that terminology myself, like on your exam, in case your professors maybe don't necessarily follow that terminology. But some people will do this though, okay? So like as an example, the matrix that we had earlier that I've been using in all the examples pretty much, it had eigenvalues of -1, 1, and 2. So this matrix A would be, you could maybe say that's indefinite right now because it has both positive and negative eigenvalues, okay? Now, however, though, if you take, if I take A and I just add 2 times the identity to it, so that just amounts to adding 2 along the diagonal. In terms of the eigenvalues, that adds 2 to all of them. So if I add 2 to these 3 eigenvalues, these would be the eigenvalues of B. So then B, being a symmetric matrix with all positive eigenvalues, B would be an example of a positive definite matrix, okay? Now, there's a theorem which allows you to check whether a symmetric matrix is positive definite without actually finding its eigenvalues, okay? So here, let's say that we have a symmetric matrix A. So because it's symmetric, it'll be the same across the diagonal like this. So I'm going to define D1 to be equal to A, this like upper left corner entry. And D2, I'm going to define D2 to be the determinant of this upper left 2 by 2 submatrix of A. Likewise, D3 is the determinant of the upper left 3 by 3 submatrix, okay? And if A were larger, there would be like a D4, D5, etc. They would be the determinants of like the upper left matrices in A, okay? So this theorem says that A is going to be positive definite if and only if all of these determinants are positive. The theorem also tells you a condition for a matrix to be negative definite. So A would be negative definite if and only if these determinants alternate in sign between negative and positive, negative, positive, negative, positive, etc. Okay. And to kind of illustrate this theorem, I have this example here. So we'll try to do this example real quick. Okay. So we have this matrix with t's in it. This is kind of similar to one of the problems in your extra assignment that you had at the end. But the question is, what values of t will make this matrix a positive definite, okay? So to answer this question, we're going to use this theorem, okay? So if I look at the upper left determinants, so d1 would just be t. d2 would be the determinant of t1, 1, 3. D3 would be like the upper left 3 by 3 submatrix, but since A is already 3 by 3, that means D3 would just be the determinant of A itself. Okay. So the theorem tells us that for A to be positive definite, all of these determinants will have to be positive, okay? So we need D1 to be positive. So therefore, we can say T needs to be greater than 0 right now, since we need D1 to be positive, okay? Now, D2, let's work out this 2 by 2 determinant real quick. It'll be 3t minus 1. And for A to be positive definite, we need D2 to be greater than 0. And lastly, for A to be positive definite, we also need D3 to be greater than 0 as well, okay? Now let's work out what this determinant is. I'll do cofactor expansion along the first row. So along the first row, I'll take t times this 2 by 2 determinant. Next, we're going to have minus 1 times, cross out the row and the column. We're going to do 1, 0, 2t. Let's see, this would be t times 3t minus 4 minus, and then this is going to be t minus 0. So it'd be minus t, okay? So it's going to be 3t squared minus 4t minus another t, so minus 5t is what I'm seeing, okay? So for A to be positive definite, we need all of these expressions to be positive, okay? Okay, so t has to be greater than 0. When we look at this condition, if I move the 1 over and then divide by 3, this one tells me that t has to be larger than 1/3, okay? And then for this last condition here, that one's a little bit more complicated, right? Because it's a quadratic. I think the way that I would handle this is I would first find where this is going to be equal to 0. So I would factor out a t from both terms. So I see that this is going to be 0 when t is 0, or when t is equal to 5/3. Okay. And I'll do what we usually do in calculus, which is I'll make a number line. And then let me see here. I'm going to take some test points. And what I'm going to do is I'm going to take my test points and plug them into here to see if it's going to be positive or negative. So if I plug in -1 for t, well, I guess that doesn't matter too much though, but I mean, I guess I'll do it anyways. So let me see, but that's going to be positive, right? 3 plus 5 is 8. Okay. I'll plug in 1 for t. So plug in 1 for t, it'd be 3 minus 5. So it's going to be negative, okay? Negative. And then finally, I guess when t is larger than 5/3, so you plug in 2 for t, it's going to be positive again. It's going to be 12 minus 10 is 2. Okay. So then this condition is equivalent to saying that t is less than 0 or t is larger than 5/3 is what this one is saying. But we need to find the values of t that would satisfy all 3 of these conditions, because all 3 of them need to be true for the matrix to be positive definite. So we need t to be like greater than 0. But we also need it to be greater than 1/3. And then we also need to be greater than 5/3. Or less than 0. That's what this one is saying. But to satisfy all 3 of these possibilities, this one can't be possible then, because we need t to be positive from the first one, so we're going to ignore this. And then for values of t that will satisfy all 3 of these conditions, essentially we need t to be greater than 5/3 then, because the values of t that are greater than 5/3, those are the ones that will satisfy all 3 of them. Okay. So then therefore, we can say that this matrix A will be positive definite if and only if t is greater than 5/3. Okay. All right. So I only have one more thing to talk about after this example, but I'll go ahead and maybe pause for the moment just to see if you guys have any questions. Okay. All right. Nope, not going to talk about cross product. I don't think cross products were ever really talked about in the class, so I don't think they would be that important. Yeah. So at least in this class, they're not super important, although in your calculus classes, the cross products may be a little bit more important. Okay. I don't necessarily see why not. I guess that is a possibility. Okay. All right. So the last topic I have is the Cholesky factorization. So if you have a positive semi-definite matrix, It turns out you can factor it as C transpose times C, where C is an upper triangular matrix. Okay. And I'm just going to do an example real quickly to show you how to compute a Cholesky factorization. I have just a little bit of the procedure written out here. So to find a Cholesky factorization, essentially you're going to find an LDU factorization of your matrix. If you guys remember that from way back towards the beginning of the semester. And when your matrix is symmetric, you guys might remember that LDU will be equal to LDL transpose. Okay. And once you get the LDL transpose decomposition, you'll be able to split the matrix D into 2 by doing like a square root, and we'll see how that works. And then that will essentially give you the C and the C transpose and the Cholesky factorization. Okay. So let's wrap things up with this example. So I kind of made a note earlier that this matrix, this symmetric matrix, is positive definite because all of its eigenvalues are positive. So I figured I would use this guy as the example down here for the Cholesky factorization. Okay, yeah. So yeah, LDU is equal to LDL transpose, but only for symmetric matrices. So if a matrix is not symmetric, it would not have an LDL transpose decomposition. It would just have an LDU, okay? It would have an LDU, which is not LDL transpose. Yeah, okay. So let's take this positive definite matrix, and in order to get the LDU or LDL transpose decomposition, you want to reduce to upper triangular by doing elimination. Now remember that for things like LU and LDU, you can't swap any rows. Essentially, you have to work with the pivot that you are starting with, okay? So like, whereas I might normally like to swap rows to get like a -1 as a pivot rather than a 3, you can't do that for LU or LDU. So I'm just going to do row 2 plus 1/3 of row 1 right now to eliminate this -1, okay? So we're going to have 2 minus 1/3. That's going to be 5/3. And -1 plus 0, so that's still -1, okay? No scaling either. So the only thing you can do is just like the elimination type operations. So just adding a multiple of a row to another row. That's all you can do for LU and LDU, okay? So like at this point, I have to use the 5/3 as the next pivot. I can't get around that. So what we'll do is we'll take row 3 and we'll add 3/5 of row 2. Okay. That should then reduce to an upper triangular. And let's see what this last entry will be. It'll be 3 minus 3/5. 3 is 15/5. So I think that's going to be 12/5, okay? Yeah, that's right, yeah. Okay. So then if you guys kind of remember how this works, L was a lower triangular matrix with 1s on the diagonal. And if it's lower triangular, that means there's 0s above the diagonal. And then you can find the rest of the entries of L from the row operations that you performed, you just want to get the multipliers that you used in each of the row operations. Now here, when we did row 2 plus 1/3 of row 1, the multiplier that we used was actually negative 1/3, because the way the book thinks of it is you did minus negative 1/3 of row 1. So the multiplier is basically the opposite of the coefficient that you have. So the multiplier is negative 1/3. So I'm going to put that into here for the 2-1 entry. Okay, 2-1 entry. Now we didn't need to do an operation to eliminate the 3-1 entry. So it's just going to remain 0 in L. For the 3-2 entry, if we go to this row operation, the multiplier that we used was negative 3/5. So I'm just kind of changing the sign. That gets you the matrix L. To get D, if you take the diagonal entries of this upper triangular matrix, those will basically give you D. Sorry, and then 0, 0, 0, 0, 0, 0, okay? And then now that you have the A and the D, that would essentially give you the LD-L transpose decomposition of A. Yes, so you can like get the matrix L by like multiplying the inverses of the elementary matrices that you used. That would be a little bit more work, I would say, though, right? So to me, the simplest way is to just like take your row operations and change the sign of your coefficients. Okay. Okay, now let me see here. Okay. What we want to do though is get the Cholesky factorization, right? So the idea of the Cholesky factorization is we can take this matrix D and we can square root it by square rooting the diagonal entries themselves. So then D is equal to the square root of D times itself, like that. So I'm taking D, I'm just splitting it as a product of its square roots. And then the idea is that each of these products will give us the C and the C transpose, okay? So to complete the problem, I just need to compute the C. So I'm just going to do the square root of D times the transpose of L. So here's the square root of D. Going to multiply that by L transposed. So I'm going to transpose the L here. And if you work out that product, it's just going to be square root of 3 will multiply. So that'll be square root of 3 plus 0 plus 0. Negative square root of 3 over 3 plus 0 plus 0. 0 plus 0 plus 0. Okay. Let me space it out a bit more. Okay. Next, we'll have like 0. Well, It's going to be upper triangular, so you don't need to worry about those. Okay, so if I do this row times this column, it's 0 plus square root of 5 over 3 plus 0. So that will be this entry here. And then second row times the third column will be 0, I guess I'll just write it out. So minus 3/5 times square root of 5 over 3 plus 0. And then lastly, third row times third column will give you square root of 12 over 5. So this is your matrix C. So you can finally factor A as C transpose. So I'm just going to transpose the C that we found. So C transpose and then times C. All right, and then with that, that would be like the Cholesky factorization of A. Okay. And I guess with that, I'm going to go ahead and stop the recording.